Okay, let's get started. Hello, everybody. Thank you for joining us and welcome to the Astro 3D ECR Astronomers in Australia seminar series. My name is Dr. Amelia Fraser-McKelvey. I'm a postdoc at the University of Western Australia as part of ICRA, and my co-chair today is Dr. Dorota Bayer, and from the Swinburne University of Technology. So before we begin, it's important for us to acknowledge the traditional custodians of the land on which we meet today. The Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing traditions of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. I'm speaking with you today from the land of the Whadjuk Noongar people. My co-chair Dorota is joining us from the land of the Wurundjeri people of the Kulin Nation. Our first speaker, Daniel Prohl, is speaking to you from the land of the Watamatagal clan of the Darug Nation. And our second speaker, Cristina Martinez Lombilla, is speaking from the land of the Bedegal people. We pay our respects to their elders, past and present, and extend that respect to all First Peoples joining us here today. So why are we here? This series is facilitated by Astro 3D, which is the ARC Centre for All-Sky Astrophysics in 3 dimensions. COVID-19 has affected our ability to travel and present at international seminars this year. Especially for us in Australia, the time zones mean that often meetings take place at 2 or 3 in the morning. Case in point, it's currently 4 a.m. for me. This lack of opportunity to network could disadvantage junior astronomers when entering the job market. This series aims to combat these issues by providing a platform for junior astronomers to present their work to the world. Just a bit of housekeeping before we begin. There's going to be 2 talks over this hour. Each talk will be 20 minutes in length with 5 minutes for questions at the end of the talk. Please save your questions until the end of the talk, and you can feel free to use the chat function to type your question in if you would rather Dorota read it out for you. The talks are being recorded and they're going to be placed afterwards on the Astro 3D YouTube channel. By being here today, you're agreeing to abide by Astro 3D's meeting code of conduct. I've already warned the speakers of this, but because of Zoom, I will need to interrupt them with 5 minutes to go in their talk. And let's move on to our second speaker for today. So our second speaker is Cristina Martinez Lombilla, and she is a postdoc at the University of New South Wales in Sydney. And she's going to be speaking to us today about unveiling the intra-group light in gamma galaxy groups with the Subaru Hyper-Suprime Cam. So Cristina, you can go ahead and share your screen and get started.
Okay, so hi everybody. First of all, thank you so much for having me here. I'm Cristina Martinez Lombilla, a postdoc at the University of New South Wales in Sydney, working with Sarah Brough. And today I'm going to talk to you about my ongoing work in which I'm trying to detect the diffuse light component within galaxy groups. To do that, I use Hyper-Suprime Cam images, and our main goal or our long-term goal is to measure how much of these lights contribute to the whole group luminosity in a representative sample systems. This work has actually 2 main goals. The first one is to be prepared for the next generation of all-sky surveys. And to do that, we are going to develop a loss of our brightness optimized detection method. And the aim is to make it as automatic as possible, so as to be used in different data sets and for large samples, as these are probably two of the main issues in the loss of our brightness studies. The second goal is to use this method to detect intragroup light in galaxy groups. So I'm going to talk a bit more about all this stuff. Current galaxy evolution studies are biased toward the high sulfur brightness galaxies and structures. So in this plot, I'm showing the limiting magnitudes of some of the main surveys as a function of the observed wavelength. The upper region of the panel corresponds to the brighter regime, which is covered by the past and current surveys. These are labeled with the solid lines joining the data points. However, the fainter regime is still not discovered. So here is where we find Euclid and the Vera Rowing Observatory, which will provide the HSC survey. And they are going to try to tackle this problem in both the optical and the infrared range. We are particularly interested in the LSST, and this is the legacy survey of space and time, as this survey will provide the deepest optical imaging in the southern sky after 10 years of continuously being observing every single night. And in order to start being prepared for it, we are going to work with data of the Subaru Hyper-Suprime Cam, in particular of the data release 2. Going back to our previous plot of the limiting magnitudes of different surveys, we can see one of the reasons why HSC data is optimal for this work. This camera reaches the deepest optical data of any current survey. And the other main reason why we use this data is because the HSC production pipeline is actually a custom version of the one of the LSST. So they share the same kind of data structure and outputs. So I have to say that we also use data from HSC regions that were in which the survey overlaps with GAMA, with the GAMA survey, in order to use their information of their catalogs, something actually similar of what Danny has been doing. So why going deeper? Why is this that important? So far, most of the galaxy evolution studies have been working with the kind of image that we see here in the image on the left. This is an SDSS image of the universe as we are used to see it, or as we were used to see it. However, after 8 hours observing with the 10.4 meter GTC telescope in Palma in Spain, we obtained the image on the right. In particular, this image reached an equivalent depth to what the LSST will get after the 10 years of survey. So we can see how literally a new universe arises. We have structures now like stellar streams, a much more evident and bigger stellar halo around the galaxy, or even new objects. This is just a visual exercise that proves the importance of low software brightness studies. And this can give us new keys to fully understand the mass assembly history of the galaxies. So our work, as I said before, is to measure the intragroup light, or IGL, but to fully understand what is it, we need first to know what is the intracluster light. The intracluster light, or ICL, is the diffuse light that spreads across the center of galaxy clusters, and it is composed by the light that comes from stars ripped out from their host galaxy due to interactions with the cluster. The ICL is actually concentrated around the center of the cluster, around the brightest cluster galaxy, or BCG, as we can see in this very beautiful image. According to the lambda cold and dark matter scenario, galaxies spend most of their lives in groups, and in fact, groups are known as the building blocks of galaxy clusters. So the intragroup light can be seen as the predecessor of the intracluster light in galaxy clusters. Both the ICL and the IGL were discovered using deep observations, and they are seen as a diffuse component in the center of the system. So why is the IGL important? The IGL is formed due to interactions between galaxies in the groups. So this light can be seen as a record of the interactions the system has undergone and how the BCG has been built over the time. Actually, when simulations of the growth of the BCGs consider that an amount of the stars that are supposed to merge with the BCG will end up actually in the diffuse component, they reach a better agreement with the observations. However, the IGL is very faint and especially hard to detect, so there are very limited works with very limited samples. Actually, it has basically been detected in dense, strong interactive groups, like, for example, compact groups, as the one we see here in this image, because the strong interactions are able to spread the diffuse material up to large distances, so we can detect it. At the same time, these groups usually, if not always, have an X-ray counterpart emission and are nearby objects. Only very few detections have been achieved in those groups, and in general with quite massive ones, quite massive systems. Taking all of this into account, our aim is to set the limits to the detection of IGL in this array, and to do that, we choose galaxy groups at low to intermediate redshifts and with different mass ranges and environments. We are working in a method to detect the IGL contribution to the total group luminosity in the most automatic way as possible. The method also allows to analyze the diffuse component and is fully Python-based. So the idea is to make it public when it is completely working. And the first step, and probably the hardest one, is to build a proper mask of the HSC reduced images. We need to mask every undesirable light for but that of the galaxies of the group. To do that, we have developed a multiple-step masking process that only requires human interaction in the initial setup and in the very last step. This is very useful when dealing with ultra-deep imaging, as doing mask is very, very hard, as even the very minor light contribution is important to take into account in order to mesh the very faint regions, such, for example, the IGL. So in this way, it's key to allow for very extended masks that cover absolutely any foreground and background object. The process is based in a hot plus cold masking mode combined with an unsorb masking. This is basically to subtract to the original image a convolved image with a Gaussian filter and apply the source detection procedure afterwards, as this is especially useful for detecting the very faint and small sources. And we use this technique for the hot component, as the cold one, the cold mask, accounts for the very bright and extended sources. But the steps are thought to be iterative, so and modular, so we can improve the mask at any step as many times as we want, always using the last best result. And also to help obtaining a very good mask, we are using a GR and I combined image, just the 3 ones added, in order to increase the signal to noise and make sure that we completely cover the whole extent of any undesirable light. In total, we build 3 masks for each group. The first one is with all the masks covered, with all the sources covered, sorry. A second one is where only the flux of the BCG is preserved, like the image that we have here on the left. The shaded regions here are the mask. And finally, a third mask that preserves the light of all the group members, as the one we have here in the panel on the right. Then we perform a second order sky correction and determine the suffer brightness limit of each image. To do that, we use elliptical isophore analysis provided by Python. This is based in the ellipse task of IRAP that most of us probably know. We extract here a very extended profile in count of the central galaxy of the group, the BCG, and we use again the GR and I combined image to increase again the signal to noise of the detection. So we also do a combined inner plus outer isophore fitting procedure in order to reach the outermost detection as possible in the external parts of the BCG. By getting the values of each isophore, but over every single band image, then using the fitting that we use for the GR and I combined band, we apply for each image then, and we could perform a second order sky subtraction to the already reduced HSC images. This second order sky correction is basically to obtain a mean value for this contribution. On the panel on the left, you can see an extended profile extracted from the red isophotes on the image. The x-axis is the semi-major value of the ellipses in pixels, and in the y-axis we have the corresponding counts. So we consider the sky as the mean value of all the orange points in the profile that are those that can be zero within errors. The good news here is that the sky values are very small and in general over 0. So that means that the sky background treatment of the HSC pipelines is not very aggressive. And it means also that it's preserving a wide range of low sulfur-brightness structures up to its photometric limits. The distribution of the background also is telling us that, as it shows a very nice Gaussian shape, as you can see in the panel on the right. And finally, using this background distribution of the pixels, we obtain the sulfur-brightness limits for each image. We basically calculate the RMS of the final masked image by randomly placing 2,000 boxes of 10 by 10 arcseconds in random places all over the image. And we obtain that for the still ongoing ultra deep survey, it's not completely finished, the sulfur-brightness limit is between 30.5 to 31 magnitudes per second square, depending on the wavelength. We then continue with the sulfur-brightness profile of the galaxies of the groups. So we basically apply the same isophoto obtained in the sky subtraction step, but now for getting the sulfur-brightness values. Here I showed one example of a BCG in a group at the redshift 0.15. The isophotos are in the panel on the left, again in red, and on the right we show the sulfur-brightness profiles for each band. Again, the x-axis is the semi-major axis values for the ellipses in pixels on the top, and also in kiloparsecs on in pixels on top. This is the sulfur-brightness value in magnitudes per second square. So here in the outer parts of the profile, we have a gray region that indicates the upper limit of the error bars in the case that we are not able to get a better approach. And then the point horizontal lines in the profiles are the sulfur-brightness limits for each band that we just measured before. The dashed sulfur-brightness profile are how the profile would look before applying any required corrections, such as, for example, the sulfur-brightness dimming, the K correction, or the galactic extinction. So this is showing that we are getting reliable data profiles down to our limits. The routines also saves the information of all the isophotos, like, for example, the ellipticity, position angle, the pixels within each ellipse, and many more properties. We follow the same methodology for the galaxies within each group. However, we found that when a few galaxies are very close by, in general, because they are interactive systems, the GAMA survey was not able to distinguish between them, and they account them as only one single source. So this is the case of this subsystem that we see here on the left. And we have developed an algorithm to determine the center position of each subcomponent and separate them to extract reliable profiles. We also mask the surrounding areas to avoid any flux overlapping. Here you can see the result of the obtained mask in the image on the left and the corresponding sulfur-brightness profile in the I band on the right. I have followed all those procedures for all the galaxies in some of the groups, taking into account their individual situations, and I can say that we have been able to get reliable profiles for each band in even small galaxies and very faint ones. So we then continue with the actual extraction of the IGL, and to do that, we use one defeating technique over an extended sulfur-brightness profile of the BCG. If we plot a radial sulfur-brightness profile from the center of a galaxy group, the IGL can be detected below 26 magnitudes per second square, probably, depending on the system. And it appears as an extra component on top of the BCG profile in its very outer regions.
4 minutes left, Cristina.
Okay, thank you. This extra component can actually be modeled as a diffuse exponential added to a circuit function. So in order to try to detect the IGL, we make a two-component one defeated over the profile, over the sulfur-brightness profiles. In the plots here, this slide, show this kind of fitting. The Sersic and exponential functions are shown in orange and blue, respectively, in each panel for each band. And the solid black curve on the back is the combined fitting over the points that are actually our observed data. It seems that we can distinguish very clearly that diffuse component that is more intense toward the redder bands, and this is actually in agreement with previous studies. However, in all the cases studied so far, we also find that a single searching fit is still a very good approach, as we can see here with the yellow line. Also, the panel residual in the bottom show that both profiles are very good and very similar. When available, we also compare our results with a single searching component previously obtained in the work of Lee Kelvin and collaborators in 2012 using the SDSS and U-curve image. This is indicated with a red curve here in these profiles for other BCG. And in all the cases, the single searching fit of Kelvin and collaborators are worse fitting than the ones that we are obtaining, and they especially fail when reaching lows of our brightness values, which is something that we would expect actually. The last part of the method is to use the values of the double component fitting to perform a 2D model of the galaxies within the group and measure the contribution of the IGL to the total luminosity of the group. We do this using the astronomical software called infit by modeling the searching component to the galaxies and obtaining just the residuals of this fitting, which is basically the diffuse component we want to measure. However, we are first trying to understand what is happening with the single searching fitting issue, because we are not still very sure that we are actually detecting intragroup light. So we want to keep testing this part of the method, and we want to test to make some further checks. We do have some evidence that make us think that there is IGL in these groups, like for example, when looking at the ellipticity values obtained from the previous fitting. We are showing this in this panel on the left. We see that the ellipticity follows the expected behavior when the IGL is present. This is that it increases when going farther away. Actually, it is increasing up to around 100 kiloparsecs. And another evidence is that we get a good two-component fitting, as we said before, and also that the exponential function contributes more in the redder bands. Also, it is worth mentioning that the method has been double tested with data from the work of Mireia Montes on the ICL detection in the cluster 85. So in order to understand what is going on, we need to keep testing the method that I said before, and in particular, the fitting part. In addition to that, a way to approach the IGL detection could be to study some groups with similar properties to the ones in which the IGL has been previously detected. In the image, you can see a possible candidate to start working with, as it presents a more compact configuration with some interactions going on there. Another possibility, in the case of the IGL still remains not clearly detectable, is to stack groups and measure the mean contribution of the diffuse component to all of them. Due to the modular nature of our method, to implement this kind of routines shouldn't add any major issues, so this can perfectly be done. Finally, and as a summary, we can say that we have developed a method to detect IGL with gamma groups from HSC data, which is adaptable to different surveys and applicable to large sample of galaxy groups, including small and low signal to noise galaxies, and also in crowded regions, which these are the key points of the method and the more important ones. We do have some evidence of IGL detection, but still not completely sure. We detect an extra component on when fitting the profiles, which is more prominent in the redder bands, and also the ellipticity is increasing, but more tests needs to be done. So if we get a clear detection of the IGL, we would like to repeat the process for a statistically significant sample of groups and to extrapolate the results for the LSST depth. So this is all on my side. Thank you so much.
Thank you very much, Cristina. Very interesting. It's very precision science that you're doing. I'll hand over to Dorota for question time.
Yes, thank you very much, Cristina. And we have a few minutes left for questions. And I can already see that 2 participants raised their hands.
Do you want me to stop the full screen mode, or it's okay like this?
I think it's okay.
Okay.
So Daniel, do you have a question?
Hi, Cristina. Thanks for the talk.
Hi.
Very nice. I have a question. So, at what point can we really be sure that you know, light from the ICL is not light from a galaxy halo, like a stellar halo? And you know, I mean, when we look at these deep images, we see that things are really not symmetric at all. Things are kind of like all over the place. So how much can we really get from doing these kind of isophoto analysis?
Yeah, I mean, that's the key, actually. I mean, very good question. I mean, it's actually very difficult. I'm still trying to get into the whole process and to understand everything, because as you said, it's very, very difficult to distinguish between them. And actually, it depends on the method. I mean, the very few works that have been done before, they have this 2 fitting component method, but also there are another some different approach. And yeah, it's very different. I think the key here is to try to find few different evidence that all of them point towards a diffuse component. So with a combination of all of that, you can be sure or more sure that you are actually detecting this diffuse component. But yeah, I think the key is to make a combination of different evidence, because it's very difficult to be sure always on when it actually one component finish and when it actually the other one starts. And I don't think that is that is what is happening. I think that they actually overlap at some point. So it's
I mean, even the 2 component fit thing seems almost an arbitrary definition, and I'm just trying to think of how you do it. It'd have to be, I suppose the whole point would be to compare with theory. So whatever technique you apply would have to be applied completely consistently with, I guess, synthetic images derived from cosmological simulations, high resolution ones.
Yeah.
Can you just do a low pass filter and say, you know, we're interested in anything with this kind of spatial frequency, rather than actually, I don't know, doing isophotes? You're interested more in kind of spatial frequencies. I don't know, it's just an idea.
Yeah, I mean, but in that case, you need, well, I would say, you need like a large sample of galaxies, right? I mean, if I understand what you're meaning.
Well, yeah, I guess if you want to do a statistical way, but yeah, I'm not sure. It's just yes. But.
Yeah, I mean, and the thing, well, you know, very good that applying for very large samples is very difficult, and also for brightness.
Yeah, sure.
So, I mean, actually, that's what I'm trying to do with this method, trying to make it the most automatic as possible to being able to do that kind of test, actually. So and regarding the comparison with the theory, this is actually very tricky thing, and that actually many people is trying to work in that on the not only with the intragroup light, but in the intracluster light, to try to find a common definition or a common way to measure it between the simulations and the observations. And actually, there is some people in the LSST collaboration that are trying to to work there, where we both are are included. So yeah, those are probably the 2 main parts and the most difficult.
Yeah, it's an interesting problem. Thank you.
Thank you.
Are there any other questions from the audience?
Can I ask one?
Yes, please.
Yeah. Hi, Cristina. Very nice presentation. Images look gorgeous. I just wanted to know whether do you find any, difference in the colors in regions of the center versus the outskirt that you're sort of detecting the intercrustal light? Have you ever chance to look at that?
Yeah, very good question. Thank you. That's actually a very good point, because the colors would give us a very good and valuable information on the outskirts and actually to distinguish between two different components. But the thing here is that to properly account for the colors and such faint regions, we need to have a very well PSF model and very extended PSF model in order to recover the PSF effect around the galaxies. So far, we don't have that. The PSFs that we have from the HSC survey are smaller, that are not able to properly account for that. So, and we do know that the PSF affect different depending on the wavelength in this imaging. So, until we don't have a better, very extended PSF that accounts for these kind of issues, we cannot be sure. I mean, we can do a color analysis, but we cannot be sure that we are doing the right thing. So this is something some groups are working for in Bristol and also in the IC in Spain. So yeah, we hope to have that kind of data. Yeah.
So just quick follow-up. When you mean by the very extended PSL, how large do you mean? I'm just curious.
Yeah, very usually of a few arc, well, quite a few arc minutes, like probably around 10 arc minutes or 20 arc minutes for a survey, because what we need is a PSF of at least 1.5 or 2 times the size of the galaxy we are studying.
Oh, okay.
So for a general survey, around, maybe around, I would say around 20 arc minutes, sorry, no, I don't know if I said arc minutes or seconds before, but it's arc minutes. So yeah, quite large. And the usual PSFs that we work with are of around 1 arc minute to, or even, I don't know, depending on the survey.
I see. Thank you very much.
Thank you.
Okay, in the interest of time, I think we'll wrap up there, but please join me in thanking our 2 speakers for today, Daniel and Cristina, both very interesting talks. Also, let's thank Dorota, my co-host, and thank you all for listening to these talks.